Hi everyone, so today I am going to talk about the Laplace transforms and its inverse property. So if you could remember from the lessons number 1, we talk about the definitions of the Laplace transforms and why do we use that Laplace transform for. So basically we use transform to transform the problems into a one that is easier to solve, and then we use the inverse transform to obtain its solutions back to the original problems. And basically the Laplace transform is that when you have the problems given to you in terms of the times domains, and you can find its frequency domains or the S domains by applying the Laplace transform process. However, the other way around, if you have the problems in the frequency domains or in the S domain, you can also be able to find the functions in the time domain back by using the inverse property. Today in this lecture, we will talk about the inverse Laplace transform. So let me go back to that, and then let me open the slide for you. Okay, so in these lessons we will talk about the inverse Laplace transform. We will focus on the partial fractions expansions and also the partial expansions when you have the improper functions, and the last one when you have one of the property which is the differentiations. So how can we apply the inverse Laplace transform to that differentiations of the functions? Okay, so in these notations, so let me remind you again. Suppose you have the functions fs here, and then you want to find the ft back, like in the above process. So you have to start with the inverse Laplace transform, and then inside the parentheses you will have the functions in the S domains, and then your solutions will be the f of t. Okay, and let's talk about the rational functions. So in order to find the partial fractions expansions, you will have to have the functions given to you in terms of the rational functions. So what rational functions mean? So basically you have the fs, and then you have let's say this one is the ps functions divided by the denominator, which is the qs function. So you have both the numerator and the denominator here. So in this case, you will have to first analyze whether the fs functions is the proper functions or improper functions first before you further continue the next process of the transform. So the functions can be proper function if and only if the degree of the ps is much lesser than the degree of the qs, whereas that functions will be the improper functions if the degree of the ps is greater than or equivalent to the degree of the qs. So if that is the case, we will have to transform that improper functions to the proper functions first, and then you can continue finding the Laplace transforms. So we will take a look at that in a minute, but first thing we will take a look in the in the proper functions first. So in the proper functions, we can also divide the partial fractions expansions into three different cases. The first one is the distinct pole, the second one is the repeated pole, and the last one is the complex pole. So we will jump into the examples of the distinct pole first. So let's name that as the first example. So when you have the fs equivalent to minus s plus 5 divided by s squared plus 5s plus 4. Okay, so let me jump to that note. Okay, so the first step that you have to do is that you have to find the root of the qs function first. So from here, as you can see, we can divide that into the two parentheses multiplied together. In other words, we have to find the terms or the roots of the QS functions first. And here we can have s plus 1 multiplied with the s plus 4. And that will be equivalent to minus s plus 5 divided by s plus 1 multiplied with the s plus 4. And then for the PS or for the nominator functions, you have two different terms multiplied together. Therefore, two different terms multiplied together, which means two different constants that you need to have. Or another way to look how many number of constants you are going to require to have in this partial fraction. You can look at the highest degree of the denominator. So as you can see here, we have maximums of 2. Therefore, it means that you need 2 different constants. Okay, so let me choose A as the first constant, and we'll have B as the second constant. And then for A, I will divide that by s plus 1 terms, and then adding up with the functions or the terms of the B divided by s plus 4. So in this case, we will have minus s plus 5 divided by s plus 1 multiplied with the s plus 4, and that's equivalent to A term plus the B terms. Alright, so next step, we will start with the minus s plus 5 divided by s plus 1 terms multiplied with the s plus 4 terms, and that's equivalent to A divided by s plus 1, and adding up with B divided by s plus 4. So let me change the color first. So next step, after we know that the function is the proper function, so you can divide that into different terms adding up together, and then the next step, you will have to multiply the denominator on the left hand side of the equations onto both sides of the expression. So you will multiply that on the left side, and also you will multiply that on the right hand side on both terms as well. So that is what you will have. And then you can see that the denominator here and that multiply functions can be eliminated, and this s plus 1 and that s plus 1 can also be eliminated, and that s plus 4 and that s plus 4 can also be eliminated as well. Therefore, on the left side of the equations, you have minus s plus number 5 equivalent to A multiplied with s plus 4, adding up with B multiplied with the s plus 1, and then you cross multiply A inside the parenthesis, B also inside the parenthesis, and here is what you will have. And then the left side here remains the same. There is no change on the left side of the expressions. And next step, so let me say that's at the step number 3, and let me name that as step number 2, and that is step number 1. You factor out into different terms. So in the step number 3 here, you will have to factor out the terms that consist of the same coefficients. So in this case, we have the maximum degree of 1s, and that is the s raised to the power of 1s. So you will look for the s power of 1s on both sides of the expressions, and you make that equivalent. Therefore, you will have minus s equivalent to as plus with the bs for 1 terms. And next, you have the constants. So you look for the constant on both sides of the expressions. You will have 5 equivalent to 4a plus b. So let's look at the first group first. So this s, and this s can be eliminated. Therefore, you will have minus 1 equivalent to a plus with b. So let me name that as expressions 1, and let me name that as the expressions number 2. And then the next step, so let me say b equivalent to minus 1, and then you move a to that side, that will be minus a. So let me name that as the expressions number 3. So if you after that, you got b equal to minus 1 minus a at the expression number 3. So you will substitute that back into the expressions number 2. And here is what you are going to have. So you will have minus 1 minus a on that side. So let me erase that label first. Okay. Right, so you will have 5 equal to 4a, and then you have minus 1, and then you have minus a. So if you move 1 to that side, you will have 5 plus 1 equal to 4a, and then minus a. So that's 6 equal to 3a. Therefore, a becomes equal to positive 2. So after you got the resolve for the a, and then next step you will substitute that back into the expression number 3. So therefore our b will be equal to minus 1 and then minus with the 2. Okay, so minus 1 minus with the 2 here. Therefore our b will be equal to minus 1 plus with minus 2. Therefore the value of the b will be equal to minus 3. So now you got the result for the a and the result for the b. So the step number 4 here, you will substitute the value of a and the value of b back into the expressions number 1. Therefore minus s plus 5 divided by s, let's say s plus 1, s plus 4 equal to 2 divided by s plus 1. So when you got the solution for both a and b, you have to substitute it back into the correct positions, otherwise your result will be wrong. So a, that is equal to 2, so 2 divided by s plus 1. And then adding up with b, which is equal to minus 3 divided by s plus 4. So minus 3 divided by s plus 4. Okay, so now you got the functions for the fs written in terms of the partial fractions, and then you can see that you got 2 plus 1 and then minus with the 3 divided by s plus 4, and that is the big F. But that is not the final answer, because you have to look for the inverse of that Laplace transform. So if you compare that property back into the times domain property, you will see that we will have suppose you have the functions ft in the time domains equal to the exponential of let's say minus t. Okay, for example, then if you apply the Laplace transform, you will have the big F that is equal to 1 divided by s plus 1. So this plus here because you have the functions of the exponential going toward the left side of the graph. So that's similar to the exponential graph. Therefore, you can compare that with the with your fs, and then you look for the f of t. Okay, so let me write that at the fs equal to 2 divided by s plus 1, and then plus minus 3 divided by s plus 4. So how about if I write 2 and then multiply with s divided by s plus 1 divided by s plus 1, and then minus 3 multiplied with 1 divided by s plus 4. So what you can see from this, you can see that we have some things that is similar to this one and similar to this one. Okay, so then your inverse Laplace transform is equal to 2 at the constant. You can just write that at the constant, and then will be multiplied with the exponential of the minus 1 multiplied with t, and then minus 3 at the constant remain the same. So you have 1 now divided by s plus 4. So your a now become the value of 4. Therefore, you will have the exponential of the value of minus 4 multiplied with t. So here is the solutions for your inverse Laplace transform of this fs. Okay, and then That is the example for the distinct pole. And next, how about if you have the functions given to you but the poles are repeated? Okay, so let's say what we have next. Okay, see, let me see that. Oops, sorry. Okay, so that's it. Our solutions is matched with the solutions in your slide. Okay, so next, if we have the repeated pole, let me write down that's at the example number 2 for you. So you will have the fx equivalent to 5x plus 16 divided by s plus 2 raised to the power of 2 multiplied with s plus 5. Okay, right. Then here we go. So in this case, first thing that you have to consider whether this big fs given to you is the proper or the improper first. What do you think? Yes, that's right. This fs here is the proper functions. This is because the degree of the denominator is much greater than the degree of the numerator. Therefore, that is the proper functions. And if that is the proper functions, so next task is that you have to find the partial fractions for each of the terms. And how to do that? You have to start with considering how many constants that will be in these questions. So if you take a look carefully in these questions, you can see that the degree of your denominator is equivalent to 3. So you have that 2 and you have that 1 and make the total of 3. So the higher degree here is equivalent to 3. Therefore, you need 3 constants. You need 3 different constants. So let me write that at the first one at the A, and the second one's adding up with the B, and the last one adding up with the C. And then you have to find the denominator for each of the constant. So the first one here, if you see from here, you can see that we have the repeated pole because the roots are the same. That is minus 2 and also minus 2. So what you're gonna do, you need to separate that into different functions. And here is what you will have. So a, let me say that a divided by s plus 2 make that square for one terms, and then you have to divide b by s plus 2 at the second one. Why is that? Because that s plus 2 has been repeated for 2 times, therefore you need to separate that. Okay, for example, let me write s plus 1. Suppose you have these kinds of functions raised to the power of 3, maybe. Okay, for example, so you have the higher degree as 3. Therefore, you need to have 3 different variables or 3 different constants. Therefore, you have a divided by s plus 3 raised to the power of 3 for one's constants, and then b divided by s plus 3 raised to the power of 2 for the second constant, and then your last constant will be s plus 3 raised to the power of 1. So in total, you need 3 different variables, just like that expressions. Okay, I hope you understand that conditions. Alright, and then next, so how about C? So if we are done with that s plus 2 theorems, so we have s plus 5 left in these expressions, and here C will be divided by s plus 5. Okay, and you can see that we have 3 different variables, so that's complete with the first step. Okay, so then your second step, you have to cross multiply s plus 2 and then that square multiplied with s plus 5 on both sides of the expressions. So here is what you will have. Okay, so let me copy that one for you first. So you have b divided by s plus 2, and then adding up with c divided by s plus 5, and then Your second method is to multiply s plus 2 square and s plus 5 on both sides of the expressions. Okay, so that is what you will have. Okay, so as you can see, that one and that one can be eliminated out. That one also can be eliminated out. And that one you have raised to the power of 1 left. So that's s plus 5 and that is the s plus 5. So now what have we left after eliminations? We have 5s plus 16 equivalent to, let me say, a multiplied with s plus 5, that's for the first term, adding up with b, and then multiply with the s plus 2 and multiply with the s plus 5 terms, and then c also multiply with the s plus 2 square, and and that's it. No more left for the part c. Okay, right, here we go. So now you got everything in your hand, and then next step, you have to cross multiply the constants inside the parentheses here. Okay, inside the parentheses here. So now we will have as multiply, adding up with 5a and then plus with the b. So inside the parentheses here, so you will have the s squared plus 7s plus 10. So the last one here will be c multiplied with s squared plus 4s plus 4. So the left side remains the same. And then you can cross b here inside the parentheses. Also c here inside the parentheses here. Okay. So you will have the as plus 5a plus with bs squared plus so let me like that. Okay, so now you will have 7 bs, and then you have additions of 10b, and then you have the additions of cs squared, and then you have the additions of 4 you have the additions of the 4s, and then you have the constant c multiplied with the s, and then you have ending up with the 4c, and the left side of the equations remains the same. So next step, so let me say that's at the step number 3. So after you cross multiply the s plus 2 square multiply with the s plus 5 on both sides of the equation, so you will have that term left. Okay, so next step, you have to look for the higher degree on both sides of the expressions, and then you match the terms that contain the same coefficients on both sides of the equations, and then you group them up. So as you can see from that expressions here, in the box, you can see that the higher degree is 2. Therefore, you have to look for the terms on both sides that consist of the degree of 2. So on the left hand side, you have 0 s squared, and that's equaling to you have this b s squared terms, this c s squared term. So you have b s squared term ending up with the c s squared term. So that's for the first group, and then the second group, that is for the 5s here. So you will have the 4s here. So let me mark at the cross. So you have the 7bs, and then you will have the 4cs. Okay, so you have the as plus 7bs, and then adding up with 4cs. And how about the last one? So you have a 16 equivalent to 5a, and then adding up with the 5a here, that 10b, and that plus 4c. Okay, so then let's look at on the first group first. So you have that s squared can be cancelled out here, therefore you have 0 equivalent to b plus c. Therefore I will write b equivalent to minus c. So you have the first conditions here for the first group, and then the second group here, the SDS here can be deleted out. Therefore you have 5 equivalent to a plus 7b, and then plus with the 4c. So for this expression, so let me name that as the expression number 2. So in that expression number 2 here, you can see that we have b, right? Therefore, we can substitute b, which is equivalent to minus c, from the first expression back into the second expression. So we will have 5 equivalent to a plus 7 multiplied with the minus c, and that's adding up with 4c. So you will have minus 7c adding up with 4c, so 5 equivalent to a, so minus 7 and then adding up with the 4, so you have minus 3c. Therefore your a is equivalent to 5 plus 3c. So let me name that as the expression number 3. So next step, you will substitute the value of b, which is equivalent to minus c, and the value of a from expression 3, which is equivalent to 5 plus 3c, back into the last group. So you will have 16 equivalent to 5. So you have a here, but that will be substituted by 5 plus 3c, and then adding up with 10 multiplied with b. So our b in this case will be changed into minus c and adding up with the 4c. So next you will plus multiply here. So 5 multiplied with 5, you have 25, and then plus with 15c and minus 10c here, and then plus 4c here. Okay. So then you will have 16 equivalent to, equivalent to 25, and that becomes 15 minus 10c, that becomes plus 5c, and that's with plus 4c. So in that case, you will have 16 equivalent to 25 plus 9c. Okay, so how about if you move minus 9c on the left side of the expressions? So here on the right hand side of the expressions, you will have 25 minus with the 17, and next step you have to find the value of c, right? So minus 9 equivalent to minus 25 minus 16, that's become 9, and therefore our c will be 9 divided by minus 9, and that's become minus 1. So therefore our c is equivalent to minus 1. And then we will substitute that c equivalent to minus 1 back into expressions number 3, and also back into expression number 1. Therefore the expression number 1, b will be equivalent to minus with minus 1. So therefore our b is equivalent to plus 1. And how about a? So we know that a is equivalent to 5 plus 3 multiplied with c, but c here is minus 1. Therefore our a is 5 minus with minus 3. So therefore the value of a here will be positive 2. Okay, so now you got the value of a, b, and c, and then next step you have to go back to the first step, and then you substitute that value of a, b, and c back into the correct positions. Okay, therefore the fourth step here, our fs is equivalent to a divided by s plus 2. Okay, s plus 2 square plus with b divided by s plus 2, and then plus c divided by s plus 5. Okay, but now we can substitute the value of a, b, and c. So let me erase that at a, that b, and that c. So now the value of a is 2, you will have 2 divided by s plus 2 square. And how about b? So b is 1. How about c? c is minus 1. Okay, so remember from the last example, so if you have the big F that is equivalent to the exponential function, so let's say e raised to the power of minus 80, then you apply the Laplace transform method, you will obtain the functions in the s domain, and that is equivalent to 1 divided by s plus a. Okay, so this one is similar to the b and the c terms. But how about the a. So the a term here, this one is, if you could remember from the lesson number 1, so when we have the value of ft, and if that is equivalent to if that is equivalent to t, okay, and then the S domains or the frequency domains by applying the Laplace transform here, which will be equivalent to 1 divided by the value of the s square. So when we have the square term here, that's similar to this one, all right? Therefore, our ft would be equivalent to 2, and then that will be multiplied with 1 divided by s plus 2. Okay, so I think I will have to rewrite that for you first. Okay, so therefore your fs would be 2 multiplied with 1 divided by s plus 2, and then the whole of that square, and plus with 1 divided by s plus 2, and minus 1 multiplied with 1 divided by s plus 5. So the last two terms that can be applied with the exponential functions, but the first term here, as you can see, so when we have the functions raised to the power of 2, that will be considered as the t. Therefore, our ft here in this case will be the constant 2 multiplied with the value of the t, and that will be multiplied with the exponential functions. So in this case, you have both the lamp functions and also the exponential functions. So you have to t multiplied with the exponential of minus 2t, and then adding up with that one will be the exponential of the minus 2t, and then minus with 1 multiplied with the exponential of the minus 5t. So that is the inverse Laplace transforms of the given fs. When you have the fs given to you and you have the repeated pole, that is how you can deal with that kind of the expressions. Okay.